today, so now we will look at the final aspect of the 2D FEM, edge based FEM, where we look at some of the numerical aspects that go into calculating the matrix elements. So far we did not talk at all about how we will calculate the matrix elements, right. We had, if you remember, a function capital phi of T and H, that is what we had said, and then later we said that when we choose a particular testing function, this would become say T m, H itself would be expanded in the basis of these T's. So, you would have to think of something like this, okay. That is what we have to worry about. So, what we did, we just left it as some expression phi of T m comma T n, but how do we actually calculate this, okay. So, there is a little bit of subtlety here which we will discuss. So, here is where we discuss the assembly of equations, you are all familiar with this. So, you notice that your matrix elements over here, these capital A's, are consisting of these kinds of terms, right, the terms underlined in green. So, they are all the coupling, we call them the coupling coefficients, so to speak, between the different T's, that is what we are interested in, okay. Now, yeah, so here is the other expression, this is the main expression that we have to keep in mind. What is the form of T itself? So, there is a curl of T and a T dot H. So, let us write that down over here. So, this is going to be equal to, there is a curl of T m dot 1 by epsilon r curl of T n minus k naught squared mu r T m dot T n. These are the kinds of terms that we have to calculate, okay. Now, T itself, if you remember, what was the form that we had for T? Let us go back to the basis functions quite a while back. Here you go, right. So, this is the form that we have, right. So, you can see that they are linear in x and y, right. So, let us go all the way back and put them down, okay. So, I had L k by, so this was T k, right, L k by 4 triangle squared, A k plus B k y, C k plus D k x, correct, where these capital A, B, C, D, they come from the coordinates of the element, right. So, it is all given to me. So, one thing, you have two terms over here, first term, second term. For the first term, I need to calculate curl of T, okay. So, when I calculate curl of T, what do you think will happen over here? So, this is a vector. To calculate curl, what do I do? X hat, y hat, z hat, x, y, z, okay. Then I put A k plus B k y and C k plus D k x 0. So, d by dx of C k plus D k x, what is that? D k constant, minus d by dy of A k plus B k y, which is B k. But basically curl of T constant, right. It is not a function of x and y, good, it is easy to integrate it, okay. What about terms like T m dot T n? What kind of expression will I have? So, you have a T m and a T n which is of this form, it has some A, B, C, D, and I am going to take the dot product, okay. So, when I take dot product means I multiply the x components, right. So, I will have y squared, x squared, and will I have a x y term? Only the x components get dotted with it. So, I will not get a x y term, but I will get a constant term x into y. We will get linear, exactly. So, basically this is going to give me a quadratic in xy. Some terms may not be there, like xy term may not be there and so on, okay. But we need not get into those specifics, okay. We will try to give a general approach. Now, if I look back at the assembly term over here, it is not just capital once I get this capital phi over here, I have to integrate it over an element. That is the integral that I have to work out, right. So, what we want is integral over an element of this phi t m dot t n dx dy, okay, where this term has constant and quadratic, up to quadratic is what we have to do, okay. So, now this element E is something that is going to be very general, right. This is going to be your very general triangle. Your CAD software has given you these coordinates x1, y1. You typically have 0 control over where these elements will be, okay. Now, what remains is to calculate this integral, and the integrand is a polynomial in general. How would you calculate this integral? Once I know how to calculate this integral, I am done.
We are calling that k0 square over t dot dn as this function phi.
What am I calling capital phi?
Capital phi is that it had 2 elements, right?
Yeah, capital phi is marked over here, right. So, mu r and epsilon k0 squared.
We are talking about that function alone, right? Tm dot d. No.
I am talking about the whole thing. This whole expression integral I have to calculate, no,
Yeah.
over space. So, now this whole expression over here in the big brackets over here is some general quadratic in x and y.
Oh, but your tm dot dn
Should be comma instead of dot. Oh, sorry. Yeah, that is a comma. Okay. So, how would we do this integral? So, we have to do what? How many dimensional integration? 2 dimensional integration. Does it look very easy? From the looks of it, no, it does not seem very easy. Do we know how to integrate over a special kind of triangle? Supposing I give you a unit triangle, okay. So, let us consider a triangle of this form. Okay, so this is 90 degrees. Let us call this, let us say u and v. Let us call this 1 0 and call this 0 1. Okay. Now, on this triangle, can you do an integral of, let us say, f of u comma v du dv, where f is some polynomial, okay, over this triangle? Do we know how to do this integral? We have all studied this sometime in early undergrad. 2-dimensional integration, how do we do? We break it up like this into a strip here, right. So, what are the limits of integration over here for v? So, what is the equation of this line? U plus v is equal to 1, right. So, if I can write this expression as integral from, so first I can integrate over, let us say, so I can, this is integral u is equal to 0 to 1, okay, and integral v is equal to 0 to 1 minus u, right. So, f of u comma v dv and du, right. So, this is how I would do it, and this is, if f is polynomial, you can see this will be very simple to calculate, right. Can I get it? Can I get a closed form expression for it if f is polynomial? Yes, you will get a closed form expression, because finally they will just be polynomials. I can integrate them, substitute the limits, and I will get it. Okay. So, in fact, turns out that if I have the most general expression like this, u to the power q v to the power p du dv over this green triangle, turns out to be a very nice expression. Okay. So, surprising that it turns out to be so simple. So, you can check, for example, if I put p is equal to 0 is equal to q. So, that is du integral du dv. What should I get? When both p and q are 0, what is it physically? half, because the area of the triangle is half, right? Which is what this expression also gives you. Okay, simple check. Okay, so we know how to integrate this triangle, but what we want is this red triangle. Can we make use of this information somehow? Perpendicular bisector of what? The red triangle is not a unit triangle. So now you want to put a perpendicular bisector from any node to the opposite edge, and then bisect it. Okay, but then it's still not unit. You are saying break up the triangle into two right angle triangles and do the integration of each other. But remember, then you also have to rotate your triangles, right? Because right now your coordinate axes are what? Your triangles are not aligned with the coordinate axis like the green triangle, right? This is your x and y. So that's not enough. And anyway, that sounds like a brute force approach. Is there something cleverer? If I want, so okay, I mean the hint that I am trying to lead you towards is change of variables. Is there a change of variables that can map the two triangles to each other? This is what I am asking. So can you map any triangle to the unit triangle? Physically, think about it. Supposing I give you, some clay, and I ask you to map it into a unit triangle. Huh? Need not have the same area. You can stretch your clay or compress your clay. So if I wanted to map this red triangle to green triangle, what is the first thing you would do?
Take x1, y1, 0, 0.
Move x1, y1 to the origin. Then, well, not projection. You would do some kind of expansion such that x2, y2 goes on the x axis, x3, y3 goes on the y axis, right? So it is in general possible. There is a, I mean, at least intuitively it should be, I mean, it sounds reasonable that there is a transformation that goes from this to this. Okay, so let's try to work that out. So x, y, let's try to write this out. Okay, this is the transformation. Okay, so well, before we come to that, so let's see. So I'll give you the answer. Turns out there is a transformation from here to here. It's called an affine transformation. How does it work? So supposing I write x is equal to x1 plus x2 minus x1 times u plus x3 minus x1 times v. Now supposing I substitute u is equal to 0, v is equal to 0. What happens? I get x1. Similarly, with the same logic, let me write y is equal to, now you can tell me what I should write here, y2 minus y1 times u plus y3 minus y1 times v. Now let's see one to one. If I put u is equal to 0, v is equal to 0, which point? x1, y1. Put u is equal to 1, v is equal to 0, right? So I will get x2, y2, and the other point 1, 0, 1, I get x3, y3. So I have got a transformation that is very neatly mapping my red triangle to the green triangle, right? Very clever. So that means I can in general convert an integral of the form f of x y dx dy. This is what I have, right? I can map this into an integral f of u v, well, maybe it's some f tilde, form might change, right, du dv, and over this green triangle. Is this right, or is there something more to it? Yeah, when you do change of, this is a transformation, I mean change of basis, whatever you want to call it, right, change of variables. When you do change of variables, what is the main thing that you should not forget? The Jacobian of the transformation, right, which is, so that Jacobian term is what will come in over here. The simplest so-called idiot check you can do is put f of x of y equal to 1. So, you will get integral dx dy is equal to integral du dv, which makes no sense, right? These two triangles have different areas. So, the Jacobian is nothing but the area of the red triangle, because integral du dv is going to give me half, which is the area of right. So, J will be half of the area. Right. Okay, so I mean this is nothing new. We have all seen this in undergrad, maybe even before undergrad, when you how to do two-dimensional integration, how to do change of variables, right. So, with this, so for example, supposing I wanted to evaluate integral x dx dy. So, what would you do? So, let us call this term say a, b, c, d. Okay, just shorthand notation, and this is the integral I want to calculate. Okay, we will get a term like x square, y square. These are the terms I will get. So, supposing I got x integrated over this triangle. So, now what is my recipe? So, x I have to write as, now substitute in terms of the new variables, right. So, this will be, so x will become x1 plus au plus bv times the Jacobian times du dv, right, and integrated now over the triangle, correct. Yeah. So, what will, I mean, so we can, is this easy to evaluate? This is very easy to evaluate, because I know the analytical expressions as given from this formula. Any power of u and v I can evaluate, so I can just substitute over here and I get it. Okay. So, in my code, when I go to evaluate the a, m, n terms, these are the tricks that I have to do. Okay. So, it is important that you let the Jacobian, so this is very, very important when you get down to implementation, you calculate the Jacobian exactly, don't try to take mod of something in between, okay, because the way the points are oriented, you may get a +1 or a -1 in the definition of Jacobian. You should not try to put an absolute value over there, let it be what it is, okay. That is the source of a lot of coding mistakes. Fine. Any other questions? I mean, any questions regarding this?
So, could you say like the formula of the Jacobian?
So, formula for Jacobian. So, the Jacobian has terms like du, sorry. So, you will have dx by du, dx by dv, dy by du, dy by dv, and determinant of this. The convention for this Jacobian differs from people to people. Some people write the transpose of this as the Jacobian or whatever, but transpose does not alter determinant.
So, the new integration limits will remain changed irrespective of
The new integration limits will be this green triangle, because we have done that mapping.
from 0 to 1 minus.
Yeah, so this sorry, not green, I should use the red font. So, red is this triangle E, right. So, I am doing this change of variables from xy to uv, right. So, the limits of integration, all those three nodes, they move to these green nodes. So, the limits of integration will be this green triangle, right, and everything is in terms of u and v. Fine. And the reason this is extremely powerful is, now I have a closed form expression for calculating the matrix elements. Imagine you have a code where there are 1,000,000 elements, and if you have a closed form expression, you just substitute it in and you get the thing. There is no added calculation needed over here. There is no quadrature rule also needed over here, right. So, in more complicated problems, you may have to use a quadrature rule for each of these million entries, right. So, that is a significant, if you had to do it 1 or 2 times, it would not matter, but if you have to do multiply by 1,000,000, the time adds up. like in your integral equation approach. There you had to calculate the matrix coefficients by using quadrature rule. The higher the order of quadrature you use, the better accuracy you got, right. So that tells you that, you know, if you wanted a very accurate answer, you would have to spend a lot of time in evaluating the matrix itself. Then you would spend time in inverting that matrix. Here you are getting a closed form expression for the entries itself. So to build the matrix is fast, the matrix is itself sparse, to solve it is also fast. So these are like double advantage of FEM methods.